So we're about to begin. Thank you very much. I hope that lunch was delicious today. And we are going to continue this afternoon with a talk from Fabien Corona. He is going to talk to us about a new feature that he has been developing as a member of the core development team for inclusion in KiCad 9. Hopefully. So please give a warm welcome to Fabien Corona.
Thank you. Hello, I'm Fabien. I'm an electrical engineer. I've been using KiCad for 10 years now, and developing and bug fixing for KiCad for something like 5 years now. First of all, I'd like to check, who knows the word creepage here? Okay. So who knows clearance? Okay. So I want to talk about a standard, the IEC 6664-1, which relates to clearance and creepages for safety. So first of all, I spent some time on clearance and creepage definition, so we all agree on what it is. Then we'll look at the requirements from the standard. We'll talk briefly about the clearance checks in KiCad, because it's good, but there are some things that we need to be careful about. And then, as Seth mentioned, I'll be talking about the development of a creepage check in PCB new, and then we'll end that talk with the next steps. So first of all, the clearance. So it's the shortest distance in the air between two conductive parts. The idea is we should have enough clearance to have to prevent electric arcs. If we have arcing, we have like a low impedance path and current can flow. This is not what we want. The clearance depends on the voltage between two nets. So it is to be calculated each net against each net. In the example here, where is my mouse? Here. So I have a switch here that can withstand 700 volts. The line is to 30 volt AC. However, it is not enough according to the standard. Why? Because something can happen. For instance, thunder. We could have thunder on the power lines, and all of a sudden, we have 3,000 volts. So here we'll have an arc, which is like roughly between 20 and 50 volts, depends on the configuration. And the person here basically takes all the voltage and gets shocked. So we need good clearance for this. Now the creepage. The creepage is another distance. The clearance was over the air. The creepage on the other side, well, it's basically walking around the PCB trying to connect two conductive parts. Just like the clearance, the creepage is to be calculated each net against each net. And a good creepage prevents arc, but also leakage currents. So let's say in this situation that I have a switch here, and this switch is on a PCB. Maybe because the PCB we are using like FA4 isolator, as insulation, sorry. Maybe there's like a very small current that can flow through the person, but well, he does not feel it. But over the time, there might be some conductive dust that accumulates on the PCB, and all of a sudden, it is not safe anymore, and this person is at risk. And that's where the IEC 6664-1 comes into play. So, first of all, the title of this standard is Installation Coordination for Equipment within Low Voltage Supply Systems. It is required for both functional and safety reasons. I expose the safety reason first, but well, if you have arcing inside your product or if you have leakage currents everywhere, bad things can happen for your functions. So function and safety. It's only a low voltage standard, so it's limited to 1000 volt AC or 1.5 kilovolt DC. We are only talking about insulation through air, no compressed gas, no liquid, no solid, no frequency isolation. And it only covers frequencies up to 30 kilohertz. This IEC standard is not the only standard that covers isolation. There are other ones, such as the UL 61010. So let's check at the clearance and creepage definition by the standard. So basically, the clearance is the line of sight between two conductive parts. If we have this is not a top view like a PCB, it's more like a side view. If we have like an object in between, the clearance would be the shortest path in the air. And if we have, and so the creepage on the other side will like follow the grooves, follow the shapes, provided that the groove width is superior to some value that depends on your application. Then we need to set minimum values. We need, what values do we pick? Basically, there's like a table which is like pages long that goes way after what I show you here, which tells you that for that many voltage, you should have this many millimeters of clearance or of creepage. I'd like to point out something. There's like two cases, homogeneous and inhomogeneous fields. Homogeneous field does not exist. It's only between infinite planes or like two spheres, the one inside the other. So basically, we're always in case A. OK, so now how do we calculate the target clearance based on the standard? It depends on many things. The first, obviously, are the voltages. But there are several voltages we can, we have to look for transient transient over voltages, temporary over voltages, recurring peak voltage, steady state. And I'll come to those in a few slides. Then we have pollution degree, how likely your PCB is to get polluted by conductive things. Environmental factors such as altitude. The higher you go, the more the clearance is, because, well, it's easier to arc at 3,000 meters than 2,000. And then we have extra requirements if this insulation is required for safety. So let's start with the transient over voltage. The transient over voltage depends on the grid. And it depends on the voltage you're receiving, as well as where you are located on the grid. Let's say like, here in Europe, we're mostly using those two. And depending on the over voltage category, we should withstand like 0.8 kilovolts, 1.5 kilovolt, 2.5 kilovolt, 4 kilovolt, etc. If we're using three-phase, it's another line. So the over voltage categories, it's basically where you're located on the line. OVC4, over voltage category 4, is for power distribution equipment, like power meters, but not power meters at home, like power meters at the plant. Overcurrent protection at the primary side, stuff like that. OVC3 is basically your circuit breakers, your electrical panel, so it's fixed installation. If you're designing a device that consumes electricity, you're most likely in OVC2, which is here. And OVC1 is basically you have no direct connection to the mains. It's like the cable is passing through you. Maybe you're doing like contactless, like magnetic field, current sensing or something. And then you can be OVC1. But most of the time you'll be over voltage category 2, which means that if you design something that is wired to the main, you should withstand at least, according to the standard, 1.5 kilovolt. So now this is basically the voltage that can be applied inside the PCB for transient. What we mean with transient over voltage are over voltage that lasts for a millisecond or less. That's how, about a millisecond or less. Temporary over voltage are slower variations like the grid tolerance or where your PSU tolerance if you have like, I don't know, like 300 volt voltage inside your product. Recurring peak voltage, it mainly depends on your electronics. Like if you have buck converters, if you have like power signal switching, you have to make sure that inside your product, there's no arc happening. So right here. Let's say this is like a simple like rectifier, so AC to DC, and we apply 4 kilovolt, and we look at how this kilovolt will go down the line with all the protection. Like here, if I have a 700 volt diode, well, maybe it will clamp at 1000 because there's a lot of current. Don't know. Depends on the diode and the application. And then we know that this resistor here, in this case, should withstand, then from this net and this net, we should be able to withstand in transient of a voltage 3 kilovolt. This diode, however, well, there's no issue here. And here, because we have the protection here, it's basically 5 volts. There's not much need for insulation, for safety, or for, well, we just need the functional isolation. We have to do this with the negative too. And then with the negative, well, this diode, that was no issue here. Well, now there's like 700 volts. So we need a clearance of 700 volts from here to here. So a clearance that corresponds to 700 volts. And so basically we do this for all the schematics. We try to group it by net classes, and we define the voltage that can come across net classes. A second example that's not related to the grid, if you have like 48 volt electromagnet and you have a transistor driving this one, when your transistor is off, well, it's holding 50 volt here, so your spacing, your clearance, and your creepage should be able to withstand 50 volt. And well, when the transistor is on, the electromagnet and the diode are holding the 40 volt, basically. So now same applies. No pollution degrees. So pollution degrees define how much, well, pollution or conductive dust can happen in your product. Pollution degree 1 does not exist in the wild. It's basically sealed electronics inside your PCB, or if you have conformal coating. Conformal coating is when you, well, coat your PCB with like special coating that withstand the dielectric field. Pollution degree 2 is basically where we are here. It's residential, offices, laboratories. We don't expect a lot of pollution except for maybe the water in the air that can get into the product from time to time due to condensation. Pollution degree 3, on the other hand, well, we expect pollution. Might it be because of the environment or because of the product itself? Maybe there are like tiny particles of metal dust flowing around. And pollution degree 4 is for mainly other electronics everywhere that there's like a permanent pollution. We can get to pollution degree 4 to pollution degree 1 by applying conformal coating. And those are basically what influence the target clearance distance. So now for the creepage, it depends on less things. First of all, the rated voltage. Now we're not talking about impulse. We're talking about what it will have to withstand for a long time. The material group, because the more your FF4 or your substrate, your insulation is, well, the less it is conductive, the better it is, basically. Again, if it's a safety insulation, well, we need extra care. And then there's the pollution degree, which I just explained. So that's on what we depend, but how do we calculate it? So answer from tables within the standard, so we can find within the standard. Or we have, since version 8, I think, a calculator for that standard, actually. So the way it works, we first need to find our input voltage we have to withstand. For this, it depends on the RMS or DC voltage of the grid and our voltage category. And then we know that we need like maybe to withstand 4 kilovolt. Then we do the analysis I showed you earlier, where we basically see how this 4 kilovolt propagates through the circuit. And maybe from one node to another one, I have like 1.5 kilovolt to withstand. And that will give me basically the clearance. For the creepage, we have the RMS voltage and the recurring peak voltage, which mainly depends on on our electronics, the one we are designing. And yeah, if we just fill all of that, we have the requirements based on the standard, as well as the minimum good width. Because, well, if we have like a path that's interrupted by a slot which is only like 0.1 millimeter, that doesn't count. We need it at least like, depends on the operation degree, but something like 1 millimeter or more. Okay, so we have two distances, clearance, creepage. What the final distance I should have between my nets? The clearance is in the air. So this is what you need in the air. And on insulating surface, you need the maximum between your creepage and your clearance. Because for instance, if you have to withstand 4 kilovolt, but you're only having a 3 volt system, well, your creepage is going to be low, but your clearance is going to be high. So you need to take the maximum of 2. And the issue arises when you try to get all the path in your product, because they can get pretty complicated. If you are like stacking boards and stuff like that, it gets pretty complicated pretty quickly. So, but I come to that later. So we're talking about safety, because the clearance might be bigger if this insulation is required for safety. So what the standard tells us is, if it's required for safety, we have to double it. Like in this case, if I need like 4 kilovolt isolation, I need a 4 kilovolt, first kilovolt isolation, and then the second one at 4 kilovolt or so. Or I can do another way, which is called a reinforced isolation, which is 6 kilovolt, because the joke is for the standard 4 plus 4 equals 6. It's basically we're getting 1 over voltage category higher, or we are getting 60% more of over voltage. In this case, we went with the higher over voltage category. So that's basically it for the standard. I mean, it's 80 pages long, so the standard is not entirely in the presentation, obviously. But now I want to talk about the clearance check in KiCad. The clearance, it should be calculated net by net, meaning that I should have a clearance from net or net class, I mean, it's more or less the same. From net class 2 to net class 1, maybe I need 0.5 millimeter. From net class 3 to net class 1, I need maybe 1 millimeter. And so in order to have something, dare I say, optimal, you need to fill the entire matrix, basically. So how do we fill the matrix? Well, there's several ways to set this matrix in KiCad. We can set it all at once, like here, with a minimum clearance. Well, this is mainly for manufacturing reasons. It's not for, you're not going to use like your clearance for high voltage everywhere. That doesn't make sense. High voltage, I mean higher than 50 volts or something. You can also try, you can, not try, but you can have like a clearance set for the entire row of the matrix using this. So this is in PCB new board editor, like the board setup. And we can use user rule to like pinpoint a very single cell. And if we have a rule for every set of net classes we have, well, we have something that is well defined. Currently, if we are doing this and we're not defining the entire matrix, we can go into issues like it is not transitive. The clearance check is not transitive. It checks against net A and B. So like here, between A and B, I have 2 millimeters. Between A only has 0.2 millimeter clearance. This one only has 0.2 millimeter clearance. But well, according to the standard, that's only 0.4 millimeter clearance, while we need 2. So this is something we need to be careful about. Is, well, at least for now, it is not transitive. So if you are playing with user rules for clearance, it can happen that you have this, and it's even worse with, I think, with floating copper, which is not assigned to any net, because I don't think there's a way at the moment to go over this. One other thing we need to be careful is we're always talking about horizontal clearance, but there's also a vertical clearance. Your FF4 cannot withstand tens of kilovolts. Like most dielectrics, most common ones, I mean, they hold like maybe 50 kilovolts per millimeter on impulse, which means that if you exceed this, you will have like a conductive path within your PCB. So in this instance, so if I have only 0.1 millimeter, maybe we should not have 6 kilovolts across this dielectric. So we should not put like live and neutral here facing each other if we have 6 kilovolt requirement. That's pretty much all for the clearance. Now here comes the creepage. There's no creepage check at the moment in KiCad, so it's an ongoing development. At the moment, we can only set it by a user rule, like this one, so only to pinpoint a single cell. But maybe in the future, we might want to have something like this, to set it for the entire net class. Doesn't really make sense to have like a creepage for the entire board. So in the future, we might want to have a graphical user interface, or maybe to have like an import from a spreadsheet, because companies love Excel files. Well, at the moment, it does not run live. We need to trigger the DRC check, but maybe in the future version, we can have something that is real time, maybe. So how does it work? Basically, it's looking for the shortest path. This is what we want. So we convert all board features, may it be bordered line, holes from footprints, if they're non-plated, everything that is basically a board edge. We convert it to nodes and weighted connections. So maybe this one here is, maybe this one is like a hole, this one is like a segment, and maybe there's like 0.5 millimeters between them. And so we do this for the entire board, and then we plug in the net class. So if we want to test like net A against net B, we have like a virtual node to hold B and A and all the elements of the net. And then we just simply try and run a shortest path algorithm, and this will be our creepage. A more visual example now. So I have this board, does pretty much nothing, just a test case. I want to know if there's like, what is the shortest path between between this net A and net B. So first of all, we build the network for the board features. Then we add the connection from the nets to the board features node, basically. And then we run the shortest path algorithm, which in this case is this one. The good thing about this is this part here can be reused because it's independent of the net. So if I add another net like net C, and I want to compute net A to net C, I can easily just reuse this part. Well, so this is basically what has been going on for the DRC check. There are some limitations, at least for the first release, because, well, it takes time to get all the cases. Like, for instance, we always think of being in 2D within the same layer, but we need to make sure that we don't have any issue from top to bottom, because, well, creepage, they can actually, well, go from top to bottom. So in the first merge, I don't know what that would be, there will most likely not be this check because it's a different paradigm and it's way more computation intensive. It's basically not something we can calculate in the first, it's an iterative process. Okay, second limitation is, I told you there's like a minimum groove width, like you cannot get away with like a 0.1 millimeter groove. It has to be wide enough so conductive dust cannot just fill it and just like go straight away. So at the moment, I do not check, but the algorithm do not check this, but I think it's up to the designer to make sure that the grooves they use for this purpose, well, they have sufficient width. And then something similar also happens with circles, like at the end of circles, when the path gets shorter than the minimum groove width, it just goes straight away. At least it should. Well, for now, it's not something we've been looking into. The idea is just to have something working and make some tests with it. So that's basically all about what's being going on, and maybe we can have a look at what we can do once we have the DRC check, or what we should do maybe. First of all, well, we need a graphical user interface for this. Having user rules is useful, but not all users are willing to use them, I guess. So first of all, everything I say for clearance also applies for clearance, for creepage, sorry, also applies for clearance. Then here we have basically our matrix, the one I talked to you about earlier. And we could have like two settings, one with conformal coating and one without conformal coating, because you can have selective conformal coating, meaning that your entire board is not under coating. And in that case, in some places of your board, you need like maybe, I don't know, 5mm creepage, and in other places you only need one. So you might need several matrices. Because, you know, Excel people, we might need to like export and import from spreadsheets. One thing that I think about is, well, we want to withstand voltages. I mean, distance is only the mean of preventing arcs due to voltages. And we have the calculations from volt to distance. So maybe what we could do is in PCB new to set the voltage requirements, like as an alternative way to do things, and then ask PCB calculator, or what's the distance, and then we get that automatically as a conversion. Another tool that we could do is like a live DRC. That would be great, and this is what it could look like, basically showing the path that do not comply with the creepage rule. And well, like for this instance, when you increase the length of the slot, we see the path moving, the path changing, and at some point it completely disappears because it is not within requirements. So, as I said, KiCad is a 2D tool, mainly. We have a 3D viewer, but we might want to make some checks on 3D. For instance, making sure that we have the correct creepage from this one to this one, from the pads, because the arc can go over the components. This one also is tricky because the pads is here. The two pads, there's a second one here. The pads are here, but there could be an arc here. But there's no copper feature for this component here. So this is basically why we need a 3D check if we want something like is really, really safe, or if you want to be maybe more compact that we can be without like having problems with clearance and creepage. This 3D check would also could also apply like to other parts, like between PCBs if you have a PCB flex, or if you have screws, because well, creepage and clearances, they don't really care if you're on your PCB, or what's very important is the entire product. And yeah, so this is not something KiCad I think should tackle because it's not a 3D engine, but maybe this is something that in the far future we could have to have those kind of checks. As a conclusion, because this comes the end of my presentation, clearance and creepage, well, it's not only for safety. It is for safety, but it's also for functional reasons. As I said, if you have arcing and like leakage currents everywhere in your board, well, bad things gonna happen. May it be like you have like a wrong sensor output or something. I mean, things can happen. And so the IEC 6664-1 defines the creepage and clearance requirements based on voltage, and so some environmental conditions. As I said, this presentation, it's only an introduction. It's not enough to, well, know the standard by itself, because the standard is 80 pages long. But we do have a PCB calculator tool for that, which allows us to, well, to know what creepage and clearances requirements are. And so at the moment, we are trying to make a creepage check in 2D work in KiCad with some limitation, but that would be a first step. And that we expected, I expected for it, if it's used, to increase the reliability of our boards because, well, there are some problems we won't have anymore. But we can't avoid all problems if we stay in 2D. We have to go, well, 3D if we want to go with a full analysis. But that's really complicated to do, and I don't see this in a near future. Maybe I'm wrong, but I don't see it right now. And so that's the end of my presentation. I don't know if you have any questions.
Thanks for the talk. I have two questions. First, is KiCad able to check the distances between the layers?
At the moment, in clearance or in creepage? In creepage, there's no check at the moment for creepage.
And clearance, you show the stack up, and does it check the clearances within the stack up?
No, because it would have to know your dielectric properties anyway, because it depends on your dielectric. And I don't think there's anything coded for that anyway. Yeah, there is. Okay.
And the second question, is it possible to check creepage or set minimum creepage within the matrix in the same net class? Because the matrix you showed, there was net class 1 to net class 2, net class 2 to net class 3, and so on, but there weren't net class 1 to net class 1. And maybe same for the clearances.
The idea, there are two things I'd like to mention. First of all, with version 9, we'll be having different net classes for a single net, which means that you can have like a net class for your electrical properties, like, I don't know, like impedance or something, and then a second net class for isolation, like the net class for the isolation matrix. The thing is, two things should only be in the same net class if they have like less than 10 volts difference. Like if I go back to 0 volt and 5 volt can be in the same net class for isolation purposes because there's no creepage or really clearance requirement apart from manufacturing between 0 and 5. I mean, except if you go like with the 10 nanometer or I don't know clearance, but that's a head case. But so basically, you should group your net classes depending on how much voltage is. Some other software, proprietary tools, they don't use the word net class for isolation, but that's the same idea. It can be like groups, like physical groups or something, but it's the same idea as net class. I just want to group all of them, and between all of them, there's no more than 10 volt difference. Okay, and so how does that group needs isolation compared to another group? So it's like group per group.
Okay, thank you, Fabien.